Hey guys, what's up? Eddie Aho here with KissAnalog.com. Today we're going to do another MicroCap video, and it's going to be another tutorial. We're going to learn some more things on the tool, but we're also going to go back and practice some of those things we've already learned, and we're going to look at a new circuit, this boost converter. Not really new. I've done several videos on this, actually this board right here. So you want to go back and look at those. I'll put links to them below so you can compare what they look like to what you're going to see on your computer. Okay? Be kind of cool. Because when I was testing this, you might have thought, God, what if you did this? What if you did this? Well, now you can do it on MicroCap. So let's go hop into this thing and check it out.
All right, guys, so today is tutorial number 3. We're going to open MicroCap 12 64-bit. Double click, comes up fast. Now I've done some video series on boost converters, so I'll put the links below so you can compare that to the simulation. Tip of the day. Pretty cool. We're going to leave that going. Okay, we're going to go to help, go down to sample circuits, and look at all these circuits. There's tons of circuits. Now these are, each one of these things I click on, look how many circuits open. So there's lots of circuits for us to play with. But let's come down to switch mode power supplies, SMPS. And we'll come over to the top one, which is converters, and then it opens up another window. And we're going to go to boost converter, and there's several boost converters in here, but we're going to grab not the voltage mode, but the current mode. And I have a video on those boost converters that talks about the difference. There we go. Now let's zoom in the window. Okay, come over here where the plus and minus magnifying glasses are, and then come to auto scale F6. All right, now look at this. This is a boost converter that Christoph Basso, I hope I pronounced that right, did in this switch mode power supply book. Great book. It's on these pages. So here, what we're going to do is I'm going to show you kind of how to move things around, and then we're going to do some simulations, okay? First of all, I'm going to grab this and just move it over here for now, okay? And I'll explain why here. Let's move it down just a little bit. See these four-way intersections? Guys, there's a thing called the art of electronics, and four-way intersections do not belong. So I'm just going to grab this guy, scoot it over. Got rid of that. No reason to argue about it. Just makes it easy to see where circuits are connected and where they're not connected. If this is connected here and that dot's gone because my circuit's really big and these dots get really small, then it may look like this wire just comes down to this resistor, this diode comes out to this load. But I can just move this over, okay? I'm going to make it look better, and then we'll talk about the circuit. Okay, now look, here's two more four ways. This one here, they're so tight. See how I hover over the line, how it highlights it, but see how short that line is? So I guess I could drag this up there and it would break that four-way. But I just want to give a little more room. So here's another thing you can do is you can hold your mouse key down, and when you go like this, whatever you're touching is going to be selected. So then, now I might pull this text away from the resistor. Let's see if it does. I'm going to click down and pull. Yeah, see, I'm not moving the resistors. So, all right, I'll just have to go back and grab them, I guess. I'm just going to give a little room, about that much maybe. And I guess maybe in this case, I'm going to pull this down. And in this case, I'm going to pull this wire up. All right, fix that one. Take this ground signal, stretch it over here. Now you can see how my rubber banding's on. Remember, that's this little button right here, rubber banding. All right, one more thing, this guy, another four-way. Let's grab this signal name. Well, I don't want to grab that, so I'll hold shift down and click on that, turns it off, and then I'll just drag all this stuff up. And I'll pull it over here so it's easier to see where it is. As a matter of fact, this voltage error, I'll show you that in a moment. Okay, now let's talk about the circuit. Input voltage, by the way, that's kind of not easy to read there, so I'll pull it away. You can see that better. Here's my input voltage. Here's my load resistor, our load, 6 ohms. V out is my signal name right here. I can pull this up if I want. Oh, no, it pulls it right down to that dot because I need to get a wire. Anyway, so here's this circuit, my control IC. This is a current mode control, so it's a current mode control IC. And this is my FET, my switching FET, my inductor that I'm charging and discharging with each cycle, and my diode. Okay, so those are the main components. But I also have a current sense resistor. When this guy turns on, he pulls current down through this current sense resistor. And look at this, we have a RC filter. So we filter out some high frequencies. But there's another resistor tied to this current sense pin. And it's called VRAMP. Maybe whoops. Now, one thing is, when I tried to click on this, this thing highlighted, so I would have known that I clicked on the wrong thing. So see how that highlights? Then I know I can pull this over. All right, and there's the little wire stub that I didn't pull, so I'll pull that over too. So we'll just pull that over, say that's VRAMP. That's my little test connector there. So what this guy is an oscillator. This is the internal oscillator to this control chip. And whoops, gotta push it back up. Okay. Kind of got everything all messed up there. And now everything's all straight. All right, so this oscillator puts out a square wave. This RC makes a triangle wave out of it. What that does is it gives me a little slope compensation. And one of the things that might be good for is during a light load, I might not have very much current here, so I might not get very much current feedback. So in a boost mode converter where I have current mode control, I have a current loop. So this is kind of like my internal current loop. And then I have a voltage loop, and that's this guy. So I have this resistor here, that's my top resistor. And then my bottom resistor. So that's a voltage divider, and it's picked up here to go in this feedback pin, which is one pin of an op amp. The other pin internally is tied to a reference, and the output is this compensation pin. Then I have the compensation network. So that kind of explains all that. Here's my output capacitor, my filtering cap, 500 microfarads. And this guy says IC, that's initial conditions is equal to 5.8 volts. And what that does for you is if you're trying to do a short simulation, you don't have to wait for so many cycles where this capacitor gets charged up where the output finally comes up to voltage. You can come up to voltage a lot quicker and make your simulation smaller if that's what you're trying to do. So you can always change this, and if we open this capacitor, you can see right here that this is where the initial conditions are. Okay, and if you look down at the bottom of this box, you can see the description and the explanation of how this works. And then there's always this help thing too. You can click on help and it'll take you to some information. All right, so let me click over here, so I deselect that, and let me click on this real quick. Now, this is a subcircuit, dot subcircuit PWMC, pulse width modulation, current mode. And then these are the pin numbers, 1, 2, 3, 4, 5, 6. Okay, and then the parameters right here. And this is all the parameters. And then these asterisks mean that these are just notes. So this is just notes. See, Christoph Basso, this is when he did it. Wow, back in 1996. Okay, but now if we come over here and we scroll down here, this is where the real magic happens. Well, here, let's keep on scrolling down. Oh, here we go, right down in here. So this is where all the nuts and bolts of this subcircuit are. Okay, so I just want to show you where that is. You don't have to worry about all this stuff, but one thing I want to point out. Okay, well, you know what? We'll talk about this next video. I'm going to do a part 2 because I just want to quickly show you some things so you can get around. This resistor, RS, this is the DC resistance of this inductor. This inductor is like an ideal inductor. Same with this capacitor. This capacitor, this resistor is the ESR. So we have 25 milliohms here. This inductor has 20 milliohms of DC resistance. Now we have a gate resistor for this FET. And the FET, if we double click it, let's see what FET this is actually. Okay, this is the IRF 7413. So we could hit that show button so we can see what that is. Oh, by the way, let's click on this guy. And I'm going to jump. Usually you think pin numbers. For some reason, in this sub-circuit, it's under pin names. The numbers of the, they gave the numbers of the pins, they put them under pin names instead of pin numbers. So let me show you. Yeah, see right there, pin 1 and 2. So there's the pin numbers. Now let's move this guy out of the way so we can see pin 3. Okay, and there's our voltage error signal. Let's just grab this guy and move it up. I'm going to move it right here. Whoops. See, I could have, I'll put this right here just so we can see where, it makes it real easy to see where that is. So this is our error signal and our compensation output, and this is our compensation parts. That's going to take a whole new video. So will this ramp and this slope compensation. But there we are. So let's just run this thing. And before we do that, one more thing. Let's look at the voltage. Now, if we look across here, we see pulse, sine, exponential. We're on piecewise linear. We're on that tab. And it's a DC 3.3 volts. Now see when I come down this window, if you look down the bottom box down here, this box down here, look there, and it kind of shows you the syntax of how you put these numbers in there if you want to put a tolerance or so on. Okay, and if you're doing an AC analysis, then you'd want a voltage in the AC. Okay, but right now we're doing this DC. Now see this stuff right here? What that is it's gonna, we're gonna look at the simulation, but basically it's gonna go from 0 to 3.3 volts, and then at 650 microseconds, it's still gonna be 3.3. So that means it's gonna be flat during that time. And then it's in 651 microseconds, 1 microsecond later, it drops to 2.9. So let's just go up and see how that works. Let's go to analysis right here. Come down to probe transient, so we can just probe around like an oscilloscope probe. Okay, let's look at the input voltage. There it is. There's our 3.3, 650 microseconds. See if I hover over it, kind of shows me that, and then it drops down. And let's just zoom in on that. So how do we do that? Magnifying glass right here, and come over here and just grab a sliver. There we go. So we could grab it again and stretch out more, but that's probably enough. Let's come up here to cursors. This guy right here, cursor mode, and put that right at the corner, 650, 3.3. There's one corner, and if I get my right cursor right there, see 651, 2.9. That's what the input looks like. Let's go look at the output. Okay, there's our output. So it's ramping up, and see how it started right down here around, you know, that's about 5.8 volts. That's where this initial conditions was, right? So it ramps up, it's got these spikes, then it comes up here and it starts to try to regulate, and then the voltage drops, but it doesn't seem to mind too much, and then it comes off and regulates. So what if we went to 1 millisecond? Let's change probe. Let's go to probe and go to limits, and let's go to 1 millisecond. So instead of this 750 microseconds, let's go 1 millivolt. 1 M. Now when I close this, it's automatically going to do it. See the spinning wheel? And there it goes. So it looks like it's regulating. Okay, now let's come up to our magnifying glass and let's zoom in on this. All right, look at that. Now, what's that peak to peak? Let's go over here and check it out. I'm going to click right there, drop down to there, and it's about 104 millivolts. And that's probably not too bad. It is a little spiky and it is kind of sharp edges. So what if I want to make that better? What I'd want to do is come over and lower my ESR of my capacitor. So let's come up to the select mode, ESR. Let's change. Well, you know what? Instead of doing it this way, I could come up here and change it here. The quicker way might be, every time you do something, it has to redo the math. That's why the spinning wheel. Okay, I'm going to come over here, and let's just change this to 5 milli. That's maybe realistic for a ceramic cap. Okay, spinning wheel, and then look at that. Look how much it dropped it, and it looks much better. So that's why you want low ESR caps on your output. We could, it looks big because we're blown in, we're zoomed in on this, but it's not too bad actually. Okay, let's clear these windows. I'm going to go to probe and delete all curves. Okay, and I want to show you something else. Let's go to the switching node. Let's go to this guy and the current sense. Let's look at those two things. So come up to voltage probe, click on this. All right, that's interesting. It kind of stopped pulsing through here because it looked like it was probably regulating, so kind of paused, I think. And then let's click on the current sense right here. It says voltage sense, but the current going to the resistor creates a voltage. And look at that. Okay, now let's come up to magnifying glass. And let's just grab a section of this. I want to show you something here. Here, let's zoom in a little closer. Okay, so this is the drain, and then it gets turned on, and when it gets turned on, it gets pulled low. You see the bottom of this thing? If I hover there, it says it's about 0.6 volts. And the bottom of this, this bottom line is 0.47, so this looks like it's dropping to about if I put the tip right there, about 0.568. So why doesn't it go to 0? Well, because there's a voltage drop across this current sense resistor right here. And that's this current sense right here. See if I go top the current sense, it's right there. Now, when I do this, it's not telling me the correct voltage because it's highlighted on this blue. So I have to come over here to the red, click on that so it's underlined. And then come up here and then hover. And so yeah, so it's about 1.2 here and about 0.58 here. And see they're on their, they have their own Y graph. So what if I come up here and here, let's come over here and click on these and make them disappear, right? Drain, there, it gets rid of them. Now let's come up to scope and come down here. Whoops, see it's not highlighted. None of these are highlighted, they're all grayed out. I have to activate this window by clicking in here. Now come up to scope and say same Y scale for each plot. Okay, now let's see what the difference is, how it plots it. There's the drain. And there's a current sense. Look, now they're on the same vertical axes, so that's going to be a different look. Let's just zoom in on that now. Okay, there's where our measurement was at one point. So let's click on that again. Okay, there you go. So the red one's the current sense, see it? And the blue one's the voltage. So the series combination is, is equal to the voltage up here. So this FET turns on, the voltage drops down, it flatlines to the voltage on the current sense. The current ramps up the inductor, so we get this nice triangular shape, and then it turns off and it drops back down. But if you look closely, you can see those lines don't quite intersect. So let's just zoom in a little bit closer. Look at that, there's some separation. When there's less current, there's not as much separation. See right here? And look how they separate more and more as the current gets higher and higher. Well, that makes sense, right? Because the RDS on of this FET, the resistance of this FET is going to drop more and more voltage as the current goes through it. And that's what we can see happening. If we wanted to measure that, let's see if we can measure that. Let's say right here, from here straight down to here, that's like 38 milli. And if I come right here, right there, well, I went a little bit too far, but it says 24. It's less than that. It's around 20 probably, but yeah. So there you go. There's two ways to do it. You can also get your cursors over here and do things like that. But okay, I think that's enough to help you get around the circuit. So you start playing. You can change the value of that inductor. Watch it. Hey, one last thing. Go to scope, and let's go to a current probe instead of a voltage probe. Oh, so we have to come over here to vertical, and let's go to current. Okay, and I just click on this inductor, and it shows me the current through it. Now let's zoom in on that thing. There you go. So see, when the FET turns off, the voltage bounces up, and that's when the current drains through the inductor going through the diode. So the current's draining through this, going out this way. Whoops. Click that. I didn't mean to. Can I undo? Yeah. Okay. So there you go. Let's zoom in just a little bit closer. So when the FET turns on, we get the current ramp up on the resistor, the current sense resistor. We also get the current ramping up through the inductor, and that's what sends the current down into the resistor. So there's the current, and you want to see the peak to peak of that, we have to come down here and highlight this. And then let's come up here to cursor mode. My left cursor I'll put down here at the bottom. My right cursor I'll put at the top. And you can see right here, it's 4.5 amps. This is 2.29, so 2.3. And if you look down here, you see the delta right here, 2.28 amps. Now, if you look over here, the average is just above 3 amps right here, probably. So there you go. Just wanted to show you how you start probing and playing with your circuit and kind of goofing off with it. Hey, and by the way, before you start messing with this, come up here to File and say Save As, okay? Now, I can't save. It's not highlighted because I have a screen. Let's turn that off. Now, look. I can go File, Save As, and then change the name of this thing to change the name so that you can play around with it. And I'm going to replace, I was playing around before, so I already have one named that, but I'm going to replace it. So there we go. So now I've saved this circuit. I can pull up this now that I've fixed all the four-way intersections and all the other stuff. So now I can play around with this. And if you guys want the next video for me to change the values to look like the circuit board that I tested in the link below, then we can see how closely this resembles that. I'll do that. And it had 12 volt input, had I think 6 microhenry inductor, and we can change the FET diode to be more like what's on the board. Current sense resistor and so on. All right. Hey, one more thing. Let me show you something. The switching frequency of this. If you come up here, see this period? 5 micro. So 100 kilohertz, okay? That's where the switching frequency is. So if you want to change that, you can play with that. But like I said, I recommend saving it before you start messing around. And I recommend saving often so you can have different versions of your circuit. Now look, once we have a circuit up like this, one last thing, look at this text mode. Look at all this stuff. There's all our parameters. So there's some interesting information for you to look at. Here's the models that we have, the FET. You know, we're going to have diode models, and here's the FET right here, the subcircuit of the FET. Okay, so I just wanted to show you that. Okay, go back to page 1, and there you go. All right, guys. Hey, hope that was interesting.
Hey, guys, so what do you think? You starting to get a little better feel for that tool, that software tool, and it's kind of cool, huh? You can see some neat things, kind of play around, makes it easy. So if you don't have the bench, or if you do have the bench and you just want to play around with the tool first, or maybe after you've done something on the bench. But I like to do some simulations on the circuit after I designed one before I go build it, because sometimes I might see something like that I wasn't expecting, or there might be something I'm just trying to work out. So usually I do simulations before I build the circuit. And when I'm reviewing a circuit like this and I want to, look at something and see why they designed it a certain way, then I like to build a simulation tool as well. It's a lot faster than, soldering, but then bench stuff is fun as well. Anyway, just another tool. So let me know what you guys think, okay? Thanks for watching. Subscribe, share, do all that kind of stuff. Hey, and thanks, patrons. Thanks for your support.